Welcome to our status session working with numerical summaries and graphical summaries for continuous variables. I'm going to continue to use the Framingham baseline dataset to illustrate the summaries for continuous variables, and I'm going to use the continuous BMI variable that we took a look at in our categorical sessions. The first thing I'm going to do is to show you how to get some numerical summaries of this variable using Stata's summary command. Stata tells us again the number of observations we have, the average or mean, the standard deviation, and then a helpful thing from the summary command is we get the minimum and the maximum of BMI. We also saw these values when we used a codebook with the dataset. There's a option on the summary command to look at a more detailed summary. The summary command with the detailed option essentially gives us 3 columns of information, although Stata doesn't actually physically delineate the columns. In the left-hand column, Stata gives us selected percentiles of the data set. For instance, we can read from this column that the 25th percentile, the first quartile Q1, is a BMI value of 22.8. The median, or 50th percentile, is a BMI value of 25.2. The 75th percentile, or third quartile Q3, is a BMI value of 28. When you're trying to use Stata to get these percentiles, be sure that you don't read too far into the middle column. Stata always gives us, with the summary detail, the 4 smallest observations in the data set and the 4 largest observations in the data set. So if you're looking for the 25th percentile, be sure you stop here in the first column at 22.8 and you don't go sliding over to 16.7. 16.7 is a very small BMI. It's the 4th smallest in this data set. In the third column, Stata gives us again the mean and standard deviation, which we saw in the brief version of this command. It repeats the number of observations and the sums of the weights. In most of the work we're going to be doing in this course, these two numbers will be the same. Stata also gives us the variance, and we know that the standard deviation is the square root of the variance. So this is about right. 4.1 is about the square root of 16.76. And 2 measures that we won't talk about that Stata is going to give us are the numerical measures of skewness and kurtosis. We'll be using the graphical displays instead to assess skewness. So the command in Stata that makes a histogram is called histogram, and all I need to do is tell Stata I want a histogram of the BMI variable. Stata will choose the number of intervals to use, called bins, and it will choose a starting point and a finishing point for the data set. For much of what we're doing, Stata's choices of the bin width will be very useful, although we will have you look in the first problem set at controlling the scale on the histogram. So you can see that Stata has labeled this graph with the body mass index label that we had for the BMI variable. You can see that there are very few BMI values in this data set over the landmark cut point of 40. We know that from when we were working with our BMI category variable. We decided that since there were so few observations above 40, we would combine them with the category from 35 to 40. You can see that these observations out here above 50 are just tiny little blips because these are individual observations. Even if we only look at the distribution below 40, you can see that the distribution of BMI values in this data set is quite skewed. There are few BMI values between 35 and 40. The value of our sample average is going to be a little bit bigger than our median because even with 4,000 observations, those really high values can affect the average, dragging it up above the median. So this is a good example of a histogram that is skewed. A way we can focus in a little more on the outliers is to use the box plot instead of the histogram. The command defaults for the box plot set up a scale that looks very similar to the histogram. Remember that one of the things we are looking at in the box plot is whether the median line in the box looks about halfway between the third quartile, the top of the box, and the first quartile, the bottom of the box. And for this data set, it does look like that the BMI distribution has a median that is roughly halfway between the first and third quartiles. If you take a look at the whisker lengths, setting aside the outliers, we don't have any outliers at the low end of the BMI values, but we do have a lot of outliers at the top of the distribution. So Stata has calculated the value for the upper fence and has decided to plot a large number of the observations as isolated circles. These are exactly the observations that we saw in the upper or right-hand tail in the histogram. This is a data set where with 4,600 observations, both the box plot and the histogram give us essentially the same information about the distribution. Remember that we've talked about how the box plot might be more useful if we didn't have such a large data set. At this point, I'm going to take a finer look at the distribution of BMIs. We concluded our first session on working with BMI categories by taking a look at the distribution separately for men and for women. A handy way to get the average and standard deviation separately for the men and the women is to use an option on the tab command. So what I'm going to ask Stata to do is to tabulate the variable sex, but to summarize the continuous variable BMI as it does this. And so what Stata produces for me is a fairly nice table giving the average and standard deviations of BMI for both the men and the women. And you can see that the average for the men at 25.95, almost 26, is higher than the average for the women. That's about 25.4. You can also see, however, that the standard deviation for the men at something like 3.39 is lower than the standard deviation for the women at 4.55. This command also gives me the mean for all the observations and the standard deviation for all the observations. If I'd like to take a look in a little more detail, the version of the summary command with the detail option that I'm going to use here is to say by this variable sex, comma sort, colon, which we use with the by prefix for a number of commands, summarize the variable BMI, but give us the details. If you take a look at this, I have a table for the men, and then Stata politely has stopped for us to take a look at that table because these tables are too long to fit in the Stata results window at once. I'm going to hit the space bar so that the table for the women prints, and then I'm going to scroll a little bit so I have most of the information I need to make a few comments about this distribution. You can see that the median for the women is 24.5, which is less than the median for the men at 25.8. And you can also see the quartiles for the men and the women. If we'd like to take all of this information about the median and the quartiles for the men and the median and the quartiles for the women and take a look at them visually, there's a version of both the histogram and the box plot command that we can use to take a look at these distributions. I can ask the histogram command to take a look at the BMIs and to make a separation by sex. This will give me a histogram side by side for the men and for the women. It's a little bit hard to see the outliers in this distribution, but if you take a very careful look at this, you can see that some of the largest values of BMI are in the graph for the women, and that there don't seem to be any little bumps in the graph between 50 and 60 for the men. This comparison of outliers can be made a little sharper if we take a look at side-by-side box plots for the men and the women. And you need to be a little careful about this because the committee that wrote Stata commands for histogram and the committee that wrote the box plot commands didn't settle on a uniform way to tell it that I want to make the distribution over the variable sex. So it was a by option with the histogram. With the graph command, it's an over option that gives me the side-by-side box plots for the men and the women. One of the valuable things we can see in this graph is that indeed the BMIs at the very high end of the distribution all belong to women. There's no BMI for the men much above 40. It's convenient that 40 was one of the default reference lines Stata chose in the box plot, so that it makes me very easy to present these data and say that almost all the BMIs over 40 in the obese class 3 are observations that come from the women. We can see this if we go back to our standard deviations. I'm going to scroll back up to the concise table. As I mentioned, the standard deviation for the women is 4.6 or 4.55. The standard deviation for the men is 3.4 or 3.39. The box plot gives us a good visual as to why the standard deviation for the women is actually larger. So when we have a variable that is continuous and we'd like to look at it across different levels of a categorical variable, we just have to remember that the Stata options aren't completely uniform for the histogram and for taking a look at the box plots. So this concludes our brief survey of numerical and graphical summaries for continuous data. I've emphasized the histogram with a data set as large as the Framingham and a box plot for any size data set with continuous variables. And these are the main graphical displays for continuous variables that we'll be using in our work throughout the course.